Hello, this is the 17th class in the physics of materials course, and today we will look at the Fermi-Dirac statistics. Okay, so the Fermi-Dirac statistics describes to us the distribution of fermions in a system at thermal equilibrium. Okay, distribution of fermions across energy levels for a system in thermal equilibrium. Okay. So, the Fermi-Dirac statistics describes the distribution of fermions across energy levels for a system that is in thermal equilibrium. For our purposes this is of relevance because the electrons that we are trying to examine, electrons in a solid that we are trying to examine, electrons qualify as fermions. They have all the characteristics that go into this terminology called a fermion. So they have half integer spin, they obey Pauli's exclusion principle, and therefore they all qualify as fermions. So we would like to see this. This of course is useful to us because then it tells us something about the behavior of those electrons, what they can do, what they can't do, what they will tend to do. So this is the basic idea that we wish to examine in detail, right. So this is the Fermi-Dirac statistics. So what are the conditions? We will just state them very briefly because we have discussed them in detail earlier. First of all, it says that the fermions obey okay. So the particles obey Pauli's exclusion principle, and therefore this description applies to them. The particles are identical and indistinguishable. So this simply means that when you have energy levels and you have a certain number of particles in one energy level and another number of particles in another energy level, simply swapping a particle between two energy levels will not is not considered as a new arrangement. Okay, so if you have n1 at energy level E1 and n2 at an energy level E2, if you simply take one particle from E1 and exchange it with a particle at E2, that is not considered as a new arrangement. So that is the important thing. We will throw it into the we will incorporate it into the mathematics as we go along. So these are the two major points. The third thing of course is that it is in thermal equilibrium, plus this is a system that is that has a fixed extent. So in other words, the number of particles in it is a constant. So therefore the total number of particles, which we will call n total, is the total number of particles, is constant, is fixed. It is in thermal equilibrium, therefore the total energy of the system E total is also fixed. Okay. So n total is fixed, E total is fixed. So this is the framework that we are operating in, and this is the framework within which this Fermi-Dirac statistics is used to describe the distribution of particles. So n total is fixed, E total is fixed, and we are basically looking for this information. What is the probability that an energy level, that a state with energy level, with energy E I is occupied. So we wish to find out what is the probability that a state with energy Ei is occupied. This is the piece of information that we wish to find out. This is the framework within which we are going to do this calculation, right. So this is how we will go about it. So as you proceed you will see how this comes about. I will point out that we are going to put down some equations and proceed step by step. Under each equation I put down, please carefully note down what are the conditions under which we are claiming that equation is operating. You can always re-examine it when you are done with the class, just to see that you understand what it means when we put down that kind of an equation, because at each stage we may make some simplification, we will sometimes eliminate some conditions, sometimes we will focus on a particular condition and so on. So it is not that as you all the equations are to be just remembered as is, please understand what are the conditions under which we are putting down those equations, alright. So the system that we are dealing with has some parameters associated with it. So we will just list those down. So we will just say that it has energy levels E0, E1, E2, E3 and so on, ER, okay. At each energy level, this is the system we are basically saying Pauli's exclusion principle applies, and for it to have any meaning there has to be a certain fixed number of states. If there are infinite states, there is no meaning in saying Pauli's exclusion. Well, even then you would say that, you know, if Pauli's exclusion principle applies, then two electrons will not have exactly the same state, will not occupy exactly the same state, where the state incorporates all of the quantum number information, okay. So we basically say that these are the energy levels. At each energy level there is a certain finite number of states, so we will just call that S0. This is the number of states available at energy level E0. S1, number of energy levels available at with energy E1. S2, S3 and SR, which is the number of states available at the energy level R, okay. So we will just say that this is the scheme that we have. Now what we so if you take our system, given that it is in thermal equilibrium and given that other constraints of the system are all fixed, the energy levels, it is a fixed volume system, it is a closed system, so the energy levels are all fixed, okay. So in our calculation, in all the calculation that we will do, upfront these numbers are all fixed. We are not specifically giving energy value in terms of joules or in terms of joules specifically, we are not explicitly saying so, but regardless the point is, for our calculation purposes these are certain fixed numbers, we have to recognize that. So this is not a variable in our calculation, it is fixed, all of these numbers are fixed. Similarly, the number of states that are available at each energy level is also fixed, okay. So what they are fixed at is another calculation which we will do later on, so that is not something that immediately concerns us. For our system this is fixed, we do not have any choice, it is fixed, okay. What is not fixed, what is variable, is the actual number of particles or number of electrons in this case that happen to be sitting at E0, E1, E2, E3 and E4 and so on. So those are N0, N1, N2, N3, Nr for the state R and so on. So this is not something that is fixed, at least as we start out the calculation. As we start out the calculation, we do not know what these values are. In other words, we can consider a variety of situations. In each of those situations the difference would be the actual value of N0 versus the actual value of N1, N2, N3 and so on. Those numbers can change, you could add some particles here, you could remove some particles here, you could add some more particles here, all of those possibilities are allowed. Whereas you cannot do that with the number of states available at the energy levels or the energy levels themselves. This is all fixed, you cannot just increase E0, you cannot increase S0 and so on. When you say E0, it is fixed E0, there is no other value it can have. S0 is also the number of states there, you cannot change that in any way. Whereas the number of particles that are sitting there, subject to the fact that it is not greater than S0, you can actually increase the number of particles or decrease the number of particles. So this is the system that we have, okay. So now we wish to know, so let us what we will do is we will start in some limited fashion, then we will in our calculation we will narrow down to a certain starting point, from there we will start, we will then write a more general equation, then we will find, so this is the layout of what we are going to do. We are going to start with a narrower focus of one particular situation, then we will write a more general equation which covers the entire arrangement that we can think of, and then we will find that even though there is a larger equation that is of interest, in that larger equation there is only one term that is of real interest. If we focus on that one term, we will get the information that we want. So we will, so even though we write a much more elaborate equation, most of that equation we can set aside. We can say that most of the equation is not, it is not necessary for us to really solve or analyze that entire equation. That one term in the equation is good enough, it is the most important term that we need to analyze. So we will focus on that one term, and our calculations will be based on that term. Okay, so that is what we will do. So what is this narrow starting point that we will start with? So our narrow starting point is that we will first say that I told you that these numbers can change, right. So n0, n1, n2, n3, n4 and so on can change. Now I will start with a situation where and we will call this a distribution. So this this entire information that you have here, I will call this n bar. Okay, so as a particular n bar, okay, or I will call this n bar I, for example. So a particular n bar implies that a particular set of n0, n1, n2, n3, n4 and a particular arrangement has been chosen. A particular combination of n0, n1, a particular set of n0, n1, n2, n3, n4 has been chosen as ni. If you change this, it will be some other n bar. Okay, so that is what we are referring to. Now I will put something down here, and then we will I will explain what it means. This is the probability, this f of E is the probability function which tells us the probability that an of EI, let us say. This is the probability that the energy this is the probability that a state at energy level EI is occupied. Okay, so this is okay, so some EI, okay, is occupied. So that is the probability that it is occupied. So this is for a particular n bar. We'll remove this I so that it doesn't confuse you at the moment. We'll leave it like that. N bar is a particular set that we have here. So this is the probability that a state at energy level EI is occupied. Now what I will say is this is a more general probability. We will narrow down, and I will put the equation down here, then we will discuss it. Okay, what I mean is this is called the conditional probability that state at energy level EI is occupied. Okay, so conditional probability okay, so this is the conditional probability that state at energy level EI is occupied. Okay, so so what this means is that you have various different n bars available to you. I am picking one particular n bar. Okay, so one particular arrangement of n bar I am picking, which means a particular set of n0, n1, n2, n3, n4 and so on. So I have so at this point I have frozen all three numbers. Right, all three numbers are, anyway these two were frozen, I have also frozen this number for this particular n bar, because I happen to deliberately choose to do so. Given that I have frozen it, what is the probability that a state at energy level E3 is occupied? It is simply the ratio of the number of particles occupying those states to the number of states that are available. Okay, so there are S3 states available, there are N3 particles occupying those states. So any one of those states if you take, okay, if there are, let us say there are 10 states here and there are 4 particles here. Okay, so the chance that a particular state at S3 is occupied is simply 40%, because there are 4 particles occupying 1 of 10 states, I mean 4 of 10 states. So that is what you have as 40%. So but that is for a particular n bar. If I change the n bar, that this number would change. At the next n bar that I select, this n3 might change to, instead of 4 it might become 7, in which case for that new n bar the probability of occupancy is 70%, right. So this when I say Ni by Si, that is for a particular n bar. So this is called conditional probability. This is just the general probability that a state at energy level Ei is occupied, and we are going to write an expression for that. This is the conditional probability that that particular state is occupied, and the condition is that this is the distribution that currently exists. So that is the condition we have placed, that is why it is called conditional probability. So this conditional is got to do with this choice of this n bar, fine. So this is the conditional probability that it exists, state of at energy level Ei is occupied. So what do we now need? So if you want to look at, if you want to know, what we are going to do now is to find what we need to do to this term so that we can end up at this term. Okay, so that is the more general statement that we wish to make. What all we have to do using this term to come up with this term. So what is it that we have to do? We have to see what is the probability that, now we have a variety of different arrangements possible, each arrangement corresponds to a set like this. So so we need one information, which is what is the probability that we are at this particular n bar, right. So I have 1000 particles, out of which I have put 10 here, I have put 100 here, I have put something here, something here, something here. In another arrangement I have put 500 here, I have put 50 here, and so on. So all these possible arrangements might exist, each of which corresponds to an n bar. So for every n bar there is a probability that you will be at that n bar, I mean as opposed to any of the number of other n bars that are possible. So we will write another equation and then we will see what it means. Again I will put down the equation, then I will describe it to you. We will say first of all that P of n bar equals W of n bar by W total. What is this? What do we mean by this? This is the probability that the system actually has that specific distribution n bar. Okay, that specific distribution n bar. What is that probability? It is the number of ways in which you can create that n bar divided by the total number of ways in which you can create any n bar, or in other words this is simply W of n bar by a sum of all the n bars. If there, let us say if we put a j across all j, okay, so n bar, so you have n1, n2, n3, so on, you have you can come up with n bar j, we will say, we will call this j for example, and this is j. So if you sum it across all the n bars, then whatever you will get is one total. Okay, so we are just interested in one of them, so we just say n bar by W total. Fine, this is the total number of ways in which you can arrange the particles across all possible combinations, all possible n bars that you can get. So all specific ways in which you can specify n1, n2, n3, n4 and so on. If you take all of that together, you can come up with one W total, of which for one of them whatever you get is up here. So this is what it is. So this is the probability that the system is at a particular state n bar. Okay. So therefore f of E, okay, is now simply I will write it down. Okay. So what it means is the general probability that an state at energy level Ei is occupied, which is this term that is there, is the term here which is the conditional probability that that particular state is occupied the condition being that the state is at the overall set is at n bar times the probability that it is at n bar, right, and summed over all possible n bars. So this takes into account all possibilities. So we will I will so I will just write it down and then we will examine this a little better, so that okay. So what we mean is, so this is f of ei. Okay, so we have all the information here. I will just restate what I have just put together here so that you follow what is being done, right. This is the probability that an energy level at that a state at energy level ei is occupied. So this is the probability, right. So this is the term that we are interested in. So this is in general, regardless of all the conditions, in all conditions taken into account, in all possible ways that the system could exist, all information put together, this is the probability that a state at energy level ei is occupied, right. Now if you go back to what we put down here, we had these three possibilities. Our energy levels are fixed, the number of states at those energy levels are fixed, but we have freedom in selecting how many particles happen to be sitting at that energy level. Okay, so we had this freedom, we can keep we do have this freedom, we can select different number of particles and then distribute them at all these energy levels. Okay, so all these values can change. So we since they can change and we have many possibilities of those changes, we started out with one such possibility which we have designated as n bar, and the minute we say n bar, that means for that instant we have frozen the values of n0, n1, n2, n3, n4 and so on. Okay. So if you want to consider the entire gamut of possibilities available to you, you have to look at all possible n bar arrangements, right, n bar meaning this collection. So this is one specification of n bar, another way you could specify it, you will call it another n bar and so on. So you have lot of possibilities of n bar, of which only one is put down on the board here, right. So what we are basically saying is that the probability that a state is occupied here of energy level, some energy level is occupied, is it is equal to the probability that it is occupied when you have specified a particular n bar times the total number of the probability that it is at that n bar, and you have to sum that up, right. So to state it again, n bar is this collection here, and since you have many such n bars, there is even associated with n bar there is a probability that you are there at that n bar, right, because you have several possibilities of n that you can, several changes you can make here. So for every given change there is a new n bar, so you have a huge number of n bars available. Given how easy or how many times you can make it that way, you can have a certain probability that you are at that particular n bar. Okay, so when we put down the terms you will see that. So all I am saying is that you have a variety of values available for n bar, and if you look at those values you will find that given that the system, this whole analysis is also based on the assumption that all the possibilities that we can think of are individually equally probable, alright. So in other words, if I come up with a particular arrangement of the system, it is just as probable as another arrangement, right. So what we are interested in is therefore to see that if you take a particular arrangement, in how many ways you can attain that arrangement. Each of those ways is equally probable, and therefore if one arrangement can occur in 10 different ways, another arrangement can occur in 100 different ways. Individually the first arrangement is equally probable as each of those 10 arrangements is as equally probable as each of those 100 arrangements, but because one can occur in 10 different ways and the other can occur in 100 different ways, the second arrangement is 10 times more probable than the first arrangement. This is the basic idea, alright. So you have 10 ways to attain n bar in a particular manner and 100 ways to attain another n bar. Each of those 10 ways is just as probable as each of those 100 ways, and therefore if you look at it taken together, this 100 ways will occur 10 times more likely than this 10 ways will occur. So this is the basic idea, okay. So we have here the probability that a state at energy level ei is occupied, that is equal to the conditional probability that a state ei is occupied, the condition being that it is at n bar, times the number of ways in which you can accomplish this n bar by the total number of ways in which you can accomplish everything, okay. So this is the information. Now what we will find is which is the basic statistical mechanics tool that we employ, is that if you look at the number of ways in which you can accomplish n bar, this term, right, you have for every arrangement there is a certain number of ways in which you can accomplish it. If you focus on this term, you will find that for every arrangement you can come up with a value of w n bar, and you will find one arrangement, one particular n bar which corresponds to a particular value of n0, n1, n2, n3, n4 and so on. That particular arrangement will be the most probable arrangement, meaning the number of ways in which you can attain that arrangement will be huge. And statistical mechanics, which operates for these kinds of system, basically says that when you identify that particular arrangement which has the maximum number of ways in which you can accomplish it, you will find that it is way more probable, significantly more probable than any other arrangement possible with any other n bar that is possible, right. Therefore at that point what you will find is that we will put that down here. I will call that most probable arrangement as n bar 0, okay. So n bar 0 is the most probable arrangement that you can get for which implies okay, n bar 0 has maximized this w n bar 0, alright. When w n bar 0 is a maximum, you will find that its value will be much higher than all the other n bars that are present in the system, all the other w n bars that are present in the system, which will imply w n bar will be approximately equal to 1, okay. When this happens and we say that in our system, given the kind of system that we deal with, the most probable arrangement will be much more probable than even the next most probable arrangement, okay. So it will be not just much more, we are talking of, we did this example right at the beginning, we did when we considered the Maxwell-Boltzmann statistics, we did this example where we found that as you increase the number of particles in the system, the most probable state in the system starts becoming more and more probable relative to all the other possible arrangements in the system. The most probable microstate becomes more and more probable than the other microstates combined, okay. And we did that for 2, 3 and 4 particles, and I basically highlighted the idea that when you go to larger and larger systems, and when you are talking of 1 mole of a solid of a material which has 10 power 23 particles, and not just 2, 3, 4 particles, 10 power 23 particles, when you go to that kind of a system, the statistical mechanics indicates that in that kind of a system, the most probable arrangement will essentially be 99.9999% probable, something like almost equal to 100% probable. All the other arrangements combined will constitute a very minuscule number of arrangements relative to the most probable arrangement, okay. So therefore statistical mechanics basically operates on the idea that the most probable arrangement has a probability of occurrence of almost equal to 1, okay. So when we do a statistical mechanical approach, what we are essentially doing is, even though the system has all the possible arrangements available to it, and in this case we mean all the possible n bars available to it, because each n bar is one arrangement, one microstate, okay. So one microstate is one n bar. Even though you have so many different possible microstates available, the most probable microstate which is n bar 0, that microstate will occur in so many ways that it will be way more likely to occur than all the other microstates in that system combined, okay. Not just the second one, not just the third one, second plus third plus fourth plus whatever it is, all the possible microstates that you can think of the system, you add them all up, the number of ways in which they can occur as a sum will be a very tiny fraction of the number of ways in which the most probable microstate can occur, okay. So we have not yet put down the equations for the manner in which we will calculate this number of ways in which the most probable microstate will occur, but this is the idea, alright. So therefore if you keep that in mind, this is when I say n bar 0, we are talking of the most occurring microstate, okay. So therefore for the most occurring microstate, that is the idea that I just mentioned, the probability that it exists will be almost equal to 1. So the number of ways in which you will accomplish the most probable microstate, which is n bar 0, divided by the total number of ways in which you can attain any microstate, okay. So this term at the in the denominator also includes Wn bar 0, it includes Wn bar 0, which is the most probable microstate, plus the second most probable microstate, plus the third most probable microstate, and so on. It is just that from the second, the term, if you set aside this term, all the other terms are a very negligible contribution to this term. So the denominator is actually the same as the numerator plus a very tiny extra term, okay. So the denominator W total is Wn bar 0 plus a very tiny amount over and above that. So therefore this ratio works out to be 1 in the most probable microstate, okay. So we are saying that if you have managed to identify that particular microstate which is the most probable microstate, then the of course that it directly means that the number of ways in which you can accomplish it is a maximum, okay. So therefore we are basically saying that when you have done that, so this is the framework, okay. So this is the equation that that helps us narrow down the calculation that we wish to do, okay. What we which is basically directly taking this equation, which is the general case. The general case is that the probability of occupancy at energy level EI in general is the probability of occupancy at energy EI given a particular arrangement times the probability that that arrangement exists. When it becomes the most probable arrangement, this ratio becomes equal to 1, okay, and in the most probable arrangement we are designating this as n bar 0, and therefore this is also n bar 0. When this ratio becomes equal to 1, essentially we are basically saying that the probability of occupancy is simply the occupancy at this particular value n bar 0, okay. So where you have already reached the maximum, okay. So that so then the sum becomes meaningless, so then you basically just directly become this probability of occupancy at EI is the probability of occupancy at EI times the at this particular condition, okay. So in principle the sum would include other terms, but all those other terms are approaching 0 relative to this term, okay. So therefore the conditional probability that a particular energy level EI, a particular state at energy level EI is occupied when you have attained the most probable distribution is therefore the actual probability that the state is occupied regardless of all conditions, okay. So this is the simplification we wish to make or we find is valid for this system, right. So now our problem now changes to like I said, we started with a narrow condition, we widened it. Our narrow condition was that we only looked at in general what is the conditional probability that a particular state at energy level EI is occupied given a particular distribution n bar. That is a narrow point or the focused point where we started our calculation. We widened that to a more general equation here, which is which gives us a more complete picture of what is the probability that state at energy level EI is occupied. Then we find that even though this complete term is the more complete whole picture of the system, most of the terms in it are negligible, so we can eliminate in fact all of those other terms. It is enough if we find out what is the probability that a state at energy level EI is occupied in the most probable distribution that exists in the system. If you find that out, you have already automatically found this out. So we have started from a focused point, come up with a larger expression out here, and from that again we find that it is enough if you just focus on a particular term. What is this? This is simply, if you compare with what we have here, it is simply Ni by Si subject to at n bar, Ni okay. So or I will put it down here, it is simply okay. So this is the final generalization that we make, or final simplification that we make. So when the distribution is that most probable distribution ni n bar naught, for that distribution, when if you know the ratio ni by si, that is equal to the probability that the state is occupied, okay. So that is the direct result of this equation here, right. So what I have written here, when distribution is ni bar naught ni by si, that is simply this term here. So this term is equal to this term, which is what is out here. So that is, so for the most probable distribution, if you know ni by si, you automatically know the probability of occupancy of an state at energy level ei subject to this conditions that we have spoken of, okay. So therefore what we now come down to is we need to find out ni by si for ni naught for this particular distribution n bar naught, okay. So if you so we only need to focus on this distribution n bar naught, and in that distribution if you know ni by si, we have got the answer that we are looking for, okay. So to do that, what we are going to do is we are simply going to look at the number of ways in which you can accomplish any one given n bar, and then maximize it to see in under what conditions you get the maximum value for this. In the calculation that we do, you will at some point you will get a value for ni by si, and that is basically all the information that we are looking for, alright. So this is the approach we are going to take, alright. So we are looking for an expression for w n bar naught. Okay. So this is the number of ways in which the most probable microstate n bar naught can be attained. This is what we are looking for, and that is the expression that we are interested in. Okay. So what do we have? We have E0 energy level, S0 is the number of states available at that energy level, and N0 is the number of particles in that particular state. Then we have E1, S1, N1, E2, S2, N2, and so on. So we will just say ER, SR, NR. So some R, we have all of this. Now this is not some arbitrary number, okay. So well, okay, we have some at this point we do not know what these numbers are. We want to see the condition under which the probability, the number of ways in which this arrangement can be attained is a maximum, okay. So we will start with so what we are saying in general is we will start like this. We will say energy level EI has SI states, and in this SI states there are NI particles. We want an expression now to see the number of ways in which we can accomplish this, okay. So number of ways in which we can do this arrangement, given that we have a particular collection of N1, N0, N1, N2, N3, N4 and so on. So to do that, first we will take any one particular energy value SI, for example here, we will see the number of ways in which this can be accomplished, right, times the number of ways in which this can be accomplished. The total number of ways in which this arrangement can be accomplished, the total number of ways in which this arrangement that I have put on the board can be accomplished is the product of the number of ways in which you can attain this times the number of ways in which you can attain this times the number of ways in which you can attain the other one, and so on, right. So the product of all the ways in which you can attain each of these combinations, given that you have selected a combination, okay. So this is the way we will go about it. So we will just take a particular case EI, energy level Ei which has Si states and Ni particles available in it. The number of ways in which you can do this is simply Si factorial by Ni factorial times Si minus Ni factorial. Why is it this? It is essentially the same as saying that you have Ni particles and Si minus Ni empty spaces, okay, because you have Si states, right, you have some number of states here, state, you have some number of particles, you have some particle here, some particle here, okay. It is the same as saying you have 2 particles and 2 empty states. In how many ways can you jumble them up? That the number of ways in which you can jumble them up are the number of unique ways in which you can attain them, and therefore that represents the number of ways in which you can accomplish that condition, right. So that is the same as so you have this is just a particular example. Si is the number of states we have, so the total number of ways in which you can arrange those Si states is Si factorial or select those states, in which Ni factorial is the number of particles that happen to be there or comes from the number of particles there and the number of vacant states that are available. So if you do this, that gives you the total number of ways in which you can attain a particular combination of Ni particles sitting in Si states, right. And I said that the for the entire, so this we will call a small w, okay. So small w for particular Ni is this one. So the total number, so this is for any one of these combinations, right, which I have put down here. Any one of those combinations can be attained for once you specify the value of Ni, you can attain it in this many number of ways. So for the overall system, given that you have N0 at E0, N1 at E1, N2 at E2 and so on, the total number of ways in which you can accomplish this is simply the product of the number of ways you can accomplish each one of them. So therefore W of N0 bar is simply the product S0 factorial by N0 factorial times S0 minus N0 factorial product times S1 factorial by N1 factorial times S1 minus N1 factorial and so on. Okay, so for the energy level E0, this is the number of ways you can accomplish the arrangement. Energy level E1, this is the number of ways you can accomplish this arrangement. Product, similar term will come for energy level E2, E3, E4, E5, so on. So this is a product of terms that look like this, right. So the way of writing it is just the way we and we discussed this earlier, just the way we write sigma for a sum, we write pi for a product. So we write Wn bar is pi over I of okay. So Wn bar naught is the total number of ways in which you can attain this particular arrangement, all things considered, okay. So all things considered meaning we have already said that this is one particular arrangement. So what is the total number of ways in which okay, we should not designate this yet as the n bar naught, we do not yet know that this is the n bar naught, we are going to find the condition under which this becomes n bar naught. So this is n bar in general, okay. So a given n bar is there, a given arrangement is there, or a given set of n0, n1, n2, n3, n4 and so on up to nr is there, okay. So a given arrangement exists for which this is the number of ways in which you can attain that arrangement, okay. So the number of ways in which you can attain the arrangement is the number of ways in which you can attain the arrangement for energy level E0 times the number of ways you can attain it for E1 and so on, and so that is pi over I this. when you maximize this and when this becomes a maximum it becomes n bar 0, alright. So our calculation is in fact our interest in fact is to maximize this, okay. So when you maximize this you will get n bar 0, alright. So that is what we are going to do. So I will just rewrite that here, this is pi over I of Si factorial by Ni factorial minus times Si minus Ni factorial. So this is the total number of ways this is the total number of ways in which the microstate n bar can be attained, alright. So this is the this is what we are looking at, and we wish to we wish to identify that particular n bar which maximizes the value of this term here, okay. So that is all that we wish to do, and when we do that the we will designate that, which we will designate so we will designate that as n bar and w n bar 0 respectively. So that is what we will do. So our calculation will proceed on this basis, and in fact I will also tell you that as we proceed through the calculation our purpose, even though this is the framework within which we are actually operating, and this is the important idea that we are following, our intent actually is in this process of identifying this n bar 0 and therefore w n bar 0, in this process at an appropriate step we will find the ratio Ni by Si, and we will corresponding to this w to this particular n bar 0, corresponding to this particular arrangement. So we will designate that as Ni 0 and Si 0, okay. So this is the probability that as energy level that a state at energy level Ei is occupied in the most probable distribution that exists within the system, okay. So that is the important thing, this is the probability that a state at energy level Ei is occupied in the most probable distribution that is available in the system. When we do this we have got the this is equal to f of E. Since it is the most probable distribution, all the other terms from the calculations that we have done so far can be neglected, and we will be able to say that this is the f of E. So this is all that we are interested in. Now in our system, so this is what we are looking at. There are two more pieces of information that are relevant in our system which we will use for our calculation. The first is that we have said right at the beginning that the system is at thermal equilibrium, which means the total energy available to the system is fixed, okay. So E total is fixed, okay. So what is E total? This is simply implies the sum of the sum of all the number of particles times the energy level that they are at, okay, sum over I. So you have Ni particles sitting at energy level Ei, so Ni Ei is the total energy of those particles at that energy because of that energy level, because of those particles at that energy level, okay. So if you sum it across all energy levels, that is the total energy of the system, right. You have a different number of particles at each energy level, at each of the different energy levels. So within that energy level, then energy available is the number of particles times that energy level. You sum it across all energy levels, that is the total energy available to the system. Since this system is at equilibrium, that total energy is fixed, we do not change the total energy. So therefore this term is a constant, alright. So that is how this is going to be, and we also said the total number of particles in the system is fixed. N total, which is the total number of particles available in the system, it is also fixed. So this is what is it in terms of what we have designated within the system, in terms of the number of in the terms of the way we have distributed the particles across the system and so on, or the state of our system. This simply means the sum over I of Ni okay. So the two constraints that we have here is that the total energy of the system is fixed, therefore the sum of the number of particles at each energy level times the energy level times that energy level, that sum is a constant because that sum is equal to the total energy of the system. So that is fixed, so that is a constant. So this is one constraint that we are placing on the system. The other constraint we are placing on the system is that the total number of particles in the system is fixed, okay. So any time you do a rearrangement, you have to remove some particles from some state to put it into another state, right. So you cannot just arbitrarily add on, you cannot arbitrarily increase the number of particles in any given energy level, they have to come from one of the other energy levels or some of those other energy levels. So therefore the total number of particles is fixed, N total is fixed, that means the sum of the number of particles at all the energy levels, which then therefore totals to the total number of particles present in the system, that is fixed, that is a constant. So our job, in fact our immediate task for example is basically to see how we can maximize this term. If you maximize this term, we are able to identify the most probable state of the system. Our task is to maximize this term here subject to the constraints that the energy is fixed, therefore this term is fixed, and this number of particles is fixed, therefore this term is fixed. So we have two sums here and you have a product here, so we want to maximize this subject to these two constraints. When we do that, we will get under the maximum conditions, under the conditions that give us the maximum number of ways we can attain a particular microstate, we will automatically find that the corresponding Ni naught by Si naught is the piece of information that we are looking for, which is simply at the end of it all is the probability that a state at energy level Ei is occupied. Okay, so that is all, finally it comes down to this, we want that one particular probability. We have a lot of equations available to us from which we have narrowed down to these three equations. If you look at focus at these three equations, we will get this term. When we have got this term, we have got the answer we are looking for, and at that point we will look at the implications of that answer. Okay. So with this we will halt this in this class. We will continue with this derivation in the next class, where we will start from this point here and we will move forward with our calculations and see how we can arrive at this by focusing on this equation here subject to these two constraints. Okay. So we will see that in the next class. Thank you.